Oh, Brunner.
Yes.
Oh, that's not far away. This
Yes.
is close to us, actually.
Yes.
We had a couple of visitors from Brunner.
Masarek University. Masarek University.
There's only one, right?
Charles, there only one university is
Yeah,
there.
yeah.
Masarek University.
Possibly.
Yes.
Possibly.
Nice to meet you too. I'm from actually KI, Computer Science Engineering.
All right.
Yes.
An emerging field.
Yes.
Uh-huh,
Of course,
uh-huh, uh-huh.
I'm working last almost 70 days.
So,
Okay, we'll talk later.
Absolutely.
welcome for the second day
Wonderful. Thank you.
of the Gyan course. So now the second day we have two lectures from 10 to already we are having we are late by 10 minutes. So for 10 to 11, then followed by high tea and then again one session. Okay, till the 12:15. Then you will have some lunch, your lunch, and then after we'll meet again from I think 2 to 3. Okay, so this is the schedule of for today. So I welcome you all. Please be stay with us. Thank you. Now I handle the things to the professor.
Okay. Thank you very much. I think I have to switch on my. All right. There we go. Okay. I guess you're all fresh today, and maybe you even remember what we did yesterday, or maybe, hopefully. No, it's working, is it? Yeah. Maybe I put it in there. All right. Yeah. So what have we been doing yesterday? We worked on what we called this exponential mapping, right, for the rigid body motions and stuff. And there were discussions and questions. How do you do this? I mean, how do you use it for real robots, for kinematic chains and so on? And that's the topic of today. It's all going to be fast, I know, because we have a limited time, but I try to at least get something conveyed to you. If you have questions, I mean, anytime, just interrupt me and we can talk about it. Did you get the slides from yesterday? Okay. Yogesh, where's Yogesh? Anyway, so supposedly you're going to get them because I sent them. Yogesh left. Okay. You get them? I mean, you should have them at one point. Okay. Yeah, I sent it to him yesterday. Maybe he will distribute them. Yep. Okay, good. Then let's maybe go into, without further ado, into what we are talking about. So essentially, you just remember, what was this matrix? How do we describe rigid body motions? In a sense that we're saying that any rigid body can be represented, kinematically at least, by a frame, right? Yeah. Haha, because you haven't been here. Yeah, let's see. Maybe this is a recap. Take this as a recap, maybe. Kind of. So you know homogeneous matrices, right? Yes, cool. So, and what is it doing? A homogeneous matrix transforms point coordinates, essentially, right? But on the other hand, it actually does describe a 60 kind of transformation, because it says one frame relative to the other frame is positioned, I mean, translated somehow and oriented somehow. And that goes into, this is encoded in a rotation matrix, or let's put here a rotation matrix and a displacement vector. I guess I don't have to call this because you know this. Okay, so, and now let's say we have a robot, right? Like an open kinematic chain for the time being. And what we're interested in is, like, we have the last link. This was the last example we had yesterday. So the forward kinematics, as they call it, right, is saying that I would like to have the end effector. So here is an end effector frame. So this is a frame that is attached to any to all of the links. But let's say there is the last one, right? So in this case we have 6. This would be F6. Okay, so F6 is attached to the end effector here. And the question is, how is this end effector frame positioned relative to the word fixed frame? Because we have one frame that is fixed to the ground, and this is also the link number 0, if you want to. Yeah, so this is the question. So, and of course we use a homogeneous matrix, and the notation was that, or the notation is that we say that we have H. This is what we introduced yesterday. So H, let's say HJI, for example, right, is the transformation from I to J. For our case now, if we say that we are interested in what we call the absolute pose, means that the pose of, I mean, pose means position and orientation, right? So the pose of a frame relative to the inertial frame. So whenever we refer to the inertial frame, which means that we have the zero index, I mean index 0 as the beginning, we just omit it because that's much easier. The 0 we can drop it. It's always like this. Maybe notation, because you haven't been here yesterday at this time. The notation goes that we have a vector, right? And the vector measures from 0 to I. So this is the source and the target, okay? And then we have, of course, the leading superscript here, which is indicating the frame in which we are representing the vector. So this is essentially it. Okay, now the question is, what can we do with these exponentials? And that's what we're going to look into today. Okay, first of all, we have to say about relative configuration. So when you take one of these metrics, let's say I'm interested in the pose of, for example, sorry, still not used to it. In the pose of link, I don't know. So I don't know, what is it now? 2, 3, 3 relative to 2, for example, right? Or 6 relative to 2. Then it's easy to do because essentially what you're doing, you combine these transformations. And maybe it's interesting, or it's good to understand or to recall what it actually means. So what is Hj doing? So Hj transforms, this was the definition, Hj transforms from frame J back to F0. Then Hi does, of course, the same, right? It goes from I to 0. Maybe you should have a picture on it. Well, Hi goes from I to 0. Hj goes from J to 0. Now, in order to go from, what is it then? From I to J, you just go from I to 0 and then back to J. And when I say go back, that means like taking the inverse of the homogeneous transformation, okay? And that's exactly what we have here. Now, if you go the other way around, if you go from J to 0, from 0 to I, then you take exactly this. And always you have to read it from right to left. This is what I said for the rotations also, because you are transforming coordinates, right? This goes from J to 0, and that goes from 0 to I. So altogether it goes from J to I, okay? And if you write it out, I mean, yesterday we had the closed form for the inverse. The closed form of the inverse matrix is, we had it in the slides. Maybe you're right. Maybe I should actually do a bit of recap from yesterday, because then I can also refer to this. Where are we? We are here somewhere. Wait. I guess we had it here. Somewhere. Yeah. Yep. So if you look, for example, what we had yesterday, so this just to recall the inverse, what we had, the inverse is just, so the good thing is for these 4x4 matrix, for the homogeneous matrices, there's a closed form of the inverse, okay? And the inverse matrix looks like this, okay? So this is all I wanted to say. So we have the transpose minus, this thing there. And if you now use this and plug it into this formula, then you take the inverse and you multiply this, you multiply these matrices, and what you get is hopefully obvious, because exactly what you would expect. What you get, for example, look at this one, for the displacement is simply the vector from what? From I to J, right? This is again the vector from I to J, represented in the, which one? In the I frame, right? Because this transforms from, I mean, Ri 0 transforms from I to 0, but the transpose goes from 0 to I. So these are expressed in the space fixed frame. So this is the vector in the space fixed frame, and then you transform it back to the frame I. And this is, of course, the relative rotation from J to I. And that's it. So essentially, this is what we have there. So I'm saying in the in Hij, we have Rij, and of course, the displacement from I to J. And that's it. So not complicated, I guess. Not so. So the important question now is, so again, what about this exponential mapping? How can we use it? So what you could say is that, of course, there is a screw coordinate vector that represents this, because we had the relative motion, because we had this Euler theorem, or there was the Chords and Mozzi Chords theorem yesterday that says any rigid body motion is a screw motion, right? And then we concluded that, okay, if this is so, then we can have a screw coordinate vector that we plug into the exponential so that we get finally out the relative motion, right? The finite motion we get via the exponential from this screw coordinate. Okay, this was the justification. And now the screw coordinate always has a form like this, right? So we have, just to repeat it, we have this unit vector that goes along the screw axis, and yet we don't know the screw axis, but there's always a screw axis. So again, this is the unit vector that goes along the screw axis, and then we need a position vector, a vector to a point on the axis, and it could be any point. And if you plug this into the exponential, what we get is the motion of the frame relative to which we are measuring actually the screw coordinate, right? So this was the basic idea. And how we did it actually, so these are the screw coordinates, right? So if you call this xi and this eta just for simplicity, then you get out the homogeneous matrix by plugging it into the exponential. Okay, this is good. Yeah, so now be more specific. And I guess I have to maybe increase the size. That should be okay. Yeah. So it's bigger. Okay, so let's now look at our systems. We have a kinematic chain, right? So a kinematic chain is essentially, as we defined it yesterday when we looked at the topology, a kinematic chain is a sequence of links or bodies, okay, connected by joints. And look at this very simple example. It's always the best example. Have a Revolute joint, for example. So we have body I minus 1 and body I. Okay, they are connected by joint I. It's always like this, because when you have an open kinematic chain, you can number them exactly like starting from 0 for the ground, and then 1 to 3 to n, and then link I is connected to its predecessor by joint I. It's always like this, right? You can always number them. That's why body I is connected to its predecessor by joint I. Okay. Anyway, so what can we do? As we said, any link, any rigid body is kinematically represented by a frame. So we are touching a frame. Okay. So Fi is actually representing the body I. And of course, you have the same on the body I minus 1. You have this is the blue one, this is the red one. Okay, so this is the predecessor of Fi. Yes, I'm interested in as we say, the absolute pose, which is Hi, the homogeneous matrix, that tells you how this frame is positioned and oriented relative to the spatial frame. Okay, which we call the pose of the body. Okay, and this is Hi, as we said. Now I like to express this in terms of an exponential. Okay, what I can do is I can, and I know that this is it's a Revolute joint, for example, or it could be any joint. Not any, but we are going to see which one. But for most of the technical joints, for all of the technical joints, we can have an exponential mapping. So what I'm interested in, or what the approach is, to say, okay, let's look at the relative motion, the relative pose of the two bodies, right, of Fi relative to Fi minus 1, and use an exponential to express this relative motion. And why I'm able to do it is obvious, hopefully, because we can easily associate a screw coordinate vector to a joint, in particular the revolute joint, because you know exactly what the screw axis, in this case just the revolute axis, is. It's the joint axis, right? Okay, so what can we do? Let's say that we define the screw coordinate vector. So again, what do we need for defining a screw coordinate vector? And I'm defining the screw coordinate vector relative to, or express it in this frame of which I'm interested in. So I'm interested in the motion of Fi relative to its predecessor. That means I'm expressing the screw coordinates in this frame, okay? So what do I need? I need the unit vector again, okay? So I need the unit vector along the, in this case, the joint axis, the revolute joint axis. And this is EI. So EI, but we have to express it in the frame I. Okay, so that's why we have EI expressed in the frame I. That's important. So the frame in which you express it as I is indicated here. Okay, what else do we need? We need the vector on to a point on the axis. Okay, measured from Fi. And just call this X. For some reasons you will see maybe later on why you call it X. It's just any name. Okay, just call it X, okay? And then the formula goes like this. You take X cross E, and that's it. And then generally, you might have a pitch, H. For the revolute, if this is really a pure revolute joint, the pitch is 0, as we said. But that might be a screw joint, right? It might be a spindle or something. So then you have a finite pitch, whatever the pitch is of the screw, okay? Yesterday, I owe you one formula because there was a question by you, I guess. What if you have a prismatic joint? Then we said, well, then mathematically we say this is an infinite pitch. Okay, but the formula looks different for the exponential. It looks actually much simpler. Anyway, this is what I have to show you still. Anyway, so this is the general thing, okay? And that's it. Good, fine. And what? I plug it into the exponential, but if I plug this into the exponential, what does it actually describe? What does the exponential of this screw coordinate tell me? What does it tell us? Huh? First of all, look at this one. I didn't talk about this. Just what is exponential of the screw coordinate defined in this way telling you? So we have been saying that, so when we introduced the exponential mapping, do we have it somewhere? Maybe from yesterday? What was it actually that we conclude that? Yeah, maybe it's here. So we have been saying that so there was one question yesterday. We have two frames, right? And I tried to describe the relative pose of the two frames by using an exponential. But essentially, it's only one frame that we're looking at. Why? Because if you look at this one, for example, right? This was how we introduced it yesterday. So you have one frame, let's say one body, one frame, and we're interested in the motion of that particular frame. And we know it's a screw motion because any motion is a screw motion. So there is a screw axis and so on and so on. All this was already told. But what is now giving you? What is the exponential giving you? It's giving you, it says here, right? It's actually describing how this frame is displaced, how this frame is moving according to the screw motion relative to where it started from. So that's why we essentially have one frame that we're looking at, but there are two instances. So if you have, and this is of course obviously, what is the exponential of the argument 0? Well, it's the identity, right? And that's why it's if you call phi the angle, for example, this frame F1 is exactly located where we start from, right? Now, if you start, doing the motion, the screw motion, then it displaces. And what we're getting is the homogeneous matrix. I mean, this X gives you the homogeneous matrix that describes the pose. I mean, imagine this is now rotated. So it's somewhere here. And this H actually describes how do you transform from the displaced one to the original one. So essentially, look at the frame, define screw coordinates, plug it into the exponential, and what you get out is the homogeneous matrix that transforms from the current back to the original. And that's the only thing you have to understand. And this answers probably this question here. What does this exponential describe? It describes actually the motion of this frame, which we're interested in, but not relative to this predecessor. It describes, the relative motion to where it started from, right? So let's say this revolute joint is starting to turn, and then this goes, okay, if it's positive, it goes somewhere back, right? It goes in the back somewhere, and then the exponential tells you the homogeneous matrix that transforms from the displaced one back to the original one. Okay, good. But this is not what I wanted. What I wanted is actually the displacement from here to here, or the other way around. Okay. But that's easy done because I just have to pre-multiply it, right? Because this is how the BI comes in. So the BI is again a homogeneous transformation matrix that is just transforming from, let's say this is they call it zero reference configuration, right? This is our snapshot of or let's say the CAD drawing, for example, if you have your drawing of a robot or something, right? This is your reference configuration. You say, okay, this is when Q is 0, all the joint angles are supposed to be zeros like this, then this is the reference configuration. Okay, so relative to, so in this reference configuration, you can define this B. This is constant because it's reference, right? Zero reference. The B describes Fi relative to Fi minus 1 in the zero reference configuration. Okay, that's nice because then the only thing you have to do, you have to transform. Yeah, it would be nice to write actually, because if this is move, if this is if this joint has been moving, this is displaced somewhere, right? And just imagine, so this is displaced somewhere. So the only thing you have to do, you have to combine the transformation from the displaced one to the original one, the reference, and then of course from the reference to the predecessor. And that's all you have to do, right? And that's why actually the only thing that you have to do is probably to combine them. So if I want to go, look at the last one. If I want to go from Fi to Fi minus 1, then eventually the final relation that you have this exponential that tells you how this guy is actually moving relative to where it started from. And then followed by the constant transformation due to the initial displacement of Fi minus 1 and Fi. And this is the Bi, okay? So this is essentially this one. Now, if you have a long chain, you have the chain consisting of, I don't know, I bodies in this case, or I joints, then you do the same. So this is this, and then the same applies, of course, to the predecessor, Fi minus 2, right? So the same story goes this. And then you just, you go up to the first one, and that's it, okay? And there we go. And that is actually the so-called product of exponential formula for the, do we have it? Yeah, for the kinematic chain. And that's a famous formula that goes back to Brockett, and you find this in all these kind of modern robotics books and blah, blah, blah. As I was saying yesterday, first of all, this is a nice expression because it's very compact. Secondly, the parameterization is pretty simple. We talked about the H parameters yesterday. The H parameters are as they are. They are, they're kind of complicated because you are restricted to a certain notation, to a certain convention. Okay, but what do you need here? So if you believe me that this makes sense, then what parameters do you need to parameterize the system? Instead of the H parameters, for example, the only things that you need is exactly what goes into the screw coordinates, which means you have this xi and you have the unit vector. And that is something that you can easily define, or that you can easily measure, because when you have a robot, you know the axis, right? And that's it. You have to know the joint axis, and then you get the unit vector, and then you can easily measure a point on it. And that could be any point. I'll give you an example later on. Okay, so now we are here in probably too fast, but anyway, this is high-speed introduction to this. And this is a formula that you find as the product of exponentials. I should have this somewhere mentioned actually, because this is an important name at least, because when you go to any of these robotics conferences or look at these books, this is what you find. So it's called the product of exponentials. All right, and this goes back to and this goes back to Roger Brockett, which is a kind of a famous roboticist. Exponentials. And it's always used, abbreviated as POE. So if you search for POE, you find a lot of papers on working on so-called POE formulations. And they use it, so the good thing is that you can use it for calibration, for example, for identification, right? Because robot calibration, what is it all about? It's about identifying these parameters correctly, because if you buy a robot, you have certain DH parameters, for example, or certain geometric parameters, but they are not, of course, your system that you bought is not perfectly like this. So you have to identify, you have to calibrate these systems, and that's and this formula is also helpful in this. Why? Because what is it then? I mean, what does calibration mean? You're interested in sensitivity. You're interested in how actually this formula would change if you slightly change these parameters. It's always like sensitivities, right? Sensitivity, you have a function, or I don't know, I mean, some relation, and you are interested in how sensitive is that function to changes of the parameters. And what do? You take the derivative, like a total derivative, right? Like this. And now the good thing is, and this is what I said yesterday, what's the good thing? Why are people in system theory so keen on using exponentials for solutions of differential equations? Because if you take the derivative of this is pretty simple, because if you take the derivative of, I don't know, this formula relative with respect to x1, for example, what do you get? You get the exponential again, because exponentials, if you take derivatives, they repeat, right? We will see this when we go. Okay. Okay, so messages. This is first of all, a compact form. This product of exponential is very compact. And secondly, the parameterization is straightforward, because it's also called a vectorial representation, because you only need vectors E and X instead of super complicated DH parameters that you have to certainly introduce and so on. But we can make it even better. So we can even make it better in the sense that we can actually get rid of this of the need of introducing body fixed frames. And how does this go? Essentially by saying, school theory is coordinate invariant. That means that you can actually use any frame to express screws. And why don't we do this? Why don't we just say, okay, I'm actually using the space-fixed inertia frame to define the screw of the joint. It's the same, right? So, okay, let's say instead of, so what did we do before? Before we said actually we are defining the screw coordinates relative to the body fixed frame, because I'm interested in the motion of the body fixed frame. Okay, that's one way of doing it. But we can also say, let's introduce the screw coordinates relative to the space fixed frame. Sounds a bit strange at the beginning, but why not? So just do it. Okay, so you have the unit vector again. It's all the same concept. It's just a different reference frame that we're using. So now the unit vector and the displacement vector the vector to a point at the axis. Now we call it y. Before it was x, now it's y. That's what you need. And you measure this again relative to a space fixed frame in the reference configuration. So you have this starting configuration where you say everything is 0, and now you measure the axis I mean the point and the unit vector, relative to the space fixed frame. And what we get, the screw coordinates, we call them y. Before we call them x, I call them y, right? Okay, and it's the same. You take the unit vector in there, and then you have the y cross e. And as I was saying, whenever we have 0 as index, we skip it, because now it would be the leading superscript would be 0. As we had here, we had the I. Okay, now I is 0, and that's why I skip it. Okay, good. Now the question again: what does actually now an exponential of this screw coordinate describe? And that's a bit of a funny outcome for the time being. So what does it describe? It's the same. I mean, you just repeat what I've been saying. What is the exponential of this screw coordinate y telling you? Again, it's a homogeneous transformation matrix. That's clear. But what does this homogeneous transformation matrix describe? It's always the pose, exactly. It's a pose. It's the pose. So what it describes is when this joint is, in this case, turning, right? Then the frame of which, the frame relative to which we have been describing the screw coordinates is displaced. So essentially what it tells you is how this frame is moving. I mean, the inertia frame is moving when the joint is turning. What I said doesn't make sense. It's correct anyway. So the correct sentence would be, it tells you how a copy of the inertia frame would be moving, right? And that's interesting, because you just have a frame, and then we say, okay, what happens if we have a screw motion? How would this frame be moving? And that is exactly what it tells you. It tells you how a copy of this inertia frame, this space fixed frame, would be moving. Okay, that's nice. But how does it help me to actually get this, to say anything about the kinematic chain? Well, it's the same story, because the only thing you have to say, okay, I have to relate that relative motion to my 0 reference configuration. And that's all you need. And oops, how was it going? And yeah, we didn't have this yet. And that's exactly what you do. Now what you do, you combine all these motions of the joints, because now you don't have an intermediate as we had here. You don't have an intermediate kind of fixed displacement, because everything is now relative to the space fixed frame. That's why you just combine them, and you can just again add them together. So multiply them together. So you combine them. So the first one, the last one, this one, if you start with I, the motion of this frame is according to this joint, the exponential of yi. Then, because it's all referring to the same frame, you can just multiply it. Then the joint I minus 1 is doing something, in particular the exponential of the I minus 1, and I mean this is here. And then you go up to I minus to I1 sorry y1, and that's it. So and then you have essentially, if you look at this one, you have essentially described what happens to the inertia frame according to or due to the motion of all the joints. Eventually, I'm not interested in the the motion of the inertia frame. So that's why I finally have to relate that motion to what I'm interested in. What I'm interested in is the motion of this frame. And that's pretty simply done, because I can just say, okay, I know how this guy is moving because of all the joint motions. But what I have to do before is actually to relate it to the initial pose of this Fi. And this is by simply saying, okay, I take this Hi at the beginning. So Hi is here, Hi0, right? And I call it Ai. So Ai is the absolute initial reference configuration. So essentially what you say, you take your system at the beginning, then you compute the the pose of Fi relative to the space fixed frame, and that's it. And then you plug in the screw coordinates in these exponentials, and then you have it. And that's the second form of the product of exponentials. Yeah, okay. So we have two versions that we can use. We have either the x or the y's. So the x coordinate, the screw coordinates, are the screw coordinates expressed relative to the body fixed frame. So you have all the all the individual frames on the bodies, and then you express the screw coordinates relative to these frames. That's one version. The other version is maybe even simpler because you don't really need them, the body fixed frame. You just express everything in the space fixed frame, and that's the second version. Okay, here. And there's of course, one application for this when you look into the forward kinematics of a robot. So what's the forward kinematic of a robot? The forward kinematics is essentially saying, I give you the joint parameters, like the joint angles, and I would like to know the pose of the terminal frame. Like there's a last, you have the robot, and then I would like to have the last one. And then you just, you don't need all these body fixed frame because they don't appear in the formulation here, right? And that's why people use it for the forward kinematics very often. Okay, now I had this simple example of a revolute joint, which always, is good to analyze, or let's say a screw joint because it could have a pitch non-zero. But for how many? But usually generally you have other joints. You have, I don't know, you have universal joints, hook joints, spherical joints like ball socket joints. There are planar joints. You go on the plane. I have a rotation about this. And you can of course generalize this because the screw coordinates can be combined, right? You can have multiple screw coordinates for a joint with multiple degrees of freedom. And how do you do this? And for which joint does it actually work? And there's a name, lower pair joints. I'm not sure if you're a mechanical engineer have heard about it. Aha, good. So a lower pair joint, also called a Rayleigh pair. Rayleigh was it sounds French, but it was a German kinematician. Yes, and for all these lower pairs, you can express the joint motion by screw motion as a screw motion. Yes, blah 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 blah. This is what I was saying. Actually, what is a Rayleigh pair? What's a lower pair? A lower pair is very simple. It's a kinematic joint. What's this? Come on. It's where am I? A lower pair. I don't see any. Do we have a definition here? Features to blah blah blah. Ah yeah, yeah. So a lower pair. There we go. A lower pair is actually a joint that is defined by surface contact. Right? So surface contact, like a revolute joint. A revolute joint is defined by surface contact. You have a cylinder, you have a hollow cylinder, and they have surface contact. Then you have the prismatic joint. You can look like this. Then you have this, they call it cylindrical joint because this is 1 degree of freedom, right? That's a prismatic joint, 1 degree of freedom. The cylindrical joint is a combination of both, right? So you can slide and you can rotate. And again, this is surface contact. And then you have the ball and socket or circle joint. Again, you have a surface contact. Everything is defined by a surface contact. A universal joint is different. That's why it's not a lower pair. A universal joint is a combination of two lower pairs, of two revolute joints, but it's not a lower pair itself, right? Because it's not defined by surface contact. It's just a combination of two, revolute joints. But why I'm telling you this is because for all these lower pairs, we can use the exponential, the screw coordinates, to formulate the motion. For the universal joint, we can not do this explicitly, but we can, of course, do it because we can just combine a revolute joint with the revolute joint. So we can still use it. But if you just say this joint as such, we cannot introduce screw coordinates, but we can introduce screw coordinates for the revolute joints and then combine them. Okay, yeah, exactly. This is, again, some pictures revolute joint, and so on, so on, so on. Yeah, and there are more joints, of course. There is this, as I mentioned, this planar joint, for example. So you can have like planar translation and a rotation about the vertical axis. Yep, and of course, this, for example, doesn't work because it's not a lower pair, because it's not defined as by surface contact. You see, this is the difference. This is not defined by surface contact. It's just a line contact in this case. Yeah, and for all these things, we have so-called subgroups, right? I'm not going into detail here. When I say subgroups, yesterday, maybe a little bit. So what we did say yesterday we said, maybe I go, makes sense, maybe to go this slide here, because here. What did we say yesterday? We said actually that these homogeneous matrices, they form a group, right? Because you multiply them, and what you get is always the same kind of thing. What if you, for example, have let's say these rotations are 1 degree rotations, like planar rotations, so about one single axis. If you again combine them, what you get is again a rotation about the same axis. So what you define in this way is a subgroup, in a sense that the spatial rotations are, the full, as we call them, SO3, like the full three-dimensional group. But if you restrict it to rotations about one axis, then you define a one-parameter subgroup, right? And that is something interesting because for those subgroups, we can define exponential mappings and use it for describing these lower pair joints. Yeah, there's much more theory behind which we are not probably interested in. Oh, I don't know what I'm doing. I always make this mistake with this there's a shortcut which I don't know, but I apparently use it. Yeah, there we go. Right. Okay. Yeah, so this is repeated from yesterday. Maybe we don't need it. Okay. Who did understand what I'm saying? I know it's not easy to get at the first sight, and it's good to repeat it again and again. And maybe it's good to really look into what happens joint by joint. So I was saying that actually the only thing you need, so let's say we want to have the homogeneous matrix of link I somewhere in the kinematic chain, and to express it by our famous product of exponential formula. And I was saying that the only thing we need is this Q coordinate. And then we plug it in here, and then we get something out. I mean, so HI would be the combination of the first one, and then the second one, and so on and so on. And this is what you believed me. I mean, at least you didn't object. But let's make it a bit more concrete. Also, maybe as a summary, before we make it concrete, what is the ingredients? What do you really need for doing this? You need only vectors again. You need just a vector to the joint axis. So you measure from here a point on a joint axis. That's easy done. And you need unit vectors to the along the joint axis. That's also what you easily can do. And the only thing additionally is that you need this the initial pose of the frame that you're interested in, which is also not difficult. But let's do this for an example. Okay. This is, by the way, this is an interesting mechanism. It's used as an remote center of motion mechanism. Something for minimal invasive surgery. You know, when you do surgery, and there's this minimal invasive. These days, you're operated by robots sometimes. So, and there's this minimal invasive surgery idea. And the idea is that, for example, look at the last part here, this one. So essentially, you have a joint axis, you have another joint axis. This is not a joint, but this is where the instruments go in, right? And all of these are intersecting somewhere here. And that's the incision point. So you get a cut in your body, and then this is where everything gets into it. And all these instruments go here. And the important point is that whatever the doctor does, and maybe you have to change orientation, they have to intersect. I mean, the intersection point has to be constant, because otherwise you would, I don't know, you would stretch the opening and so on. That's not good. That's the background anyway. And this part is just to position the first part, because this is the remote center of motion mechanism. So because the point is always constant, but you have to place it to the patient and so on. And this is why we need this stuff here. Right. Okay. Number one, what's the consequence of moving the first joint? So we have 1, 2, 3, 4, 5 joints. Okay. So what's the consequence? What happens if you move joint 1? And I'm asking, before you answer, and I'm asking, what is the exponential? What is this x y1? How do we call it? phi1 maybe. What is this doing? So what's the consequence of this first exponential? Well, first of all, you have to maybe repeat your answer that you didn't give me, but I gave it to you. What is this exponential doing? That's absolutely right, but this is not specific. Of course, it's transforming a frame because it comes a frame transformation. It's easy. It's obvious. I mean, it's all here. The only question you have to ask when you have this exponential, you only have to look at the argument. What goes into the exponential? So what goes into the exponential? It's this y1. So now, what is y1? Y1 is this co-coordinate expressed in the space fixed frame. So it tells you about the motion of the space fixed frame, a copy of the space fixed frame due to the motion of the joint 1. So this is my space fixed frame. So I'm expressing all these co-coordinates of the, how many? 6, 7 joints? 1, 2, 3, 4, 5 joints, 5 joints, relative to the space fixed frame. So what's happening when I move joint number 1? Huh? Yep, I guess you are right. So it's doing like this. Is that so? Yeah. So the green one, actually, you're right, but not correctly, because you have been saying the space fixed frame is rotating. It's actually a copy of the space fixed frame, which is attached to the first link, which is the green one, right? That is moving. That's what you see. Okay. What about the second joint? What happens if I move this joint? Which one is rotating? So another copy of this frame. Of this frame. Okay. Right, exactly. Why? Because I was saying, I mean, you're right, but why is it correct? Because I was saying, actually, now we look at this second one, right? So this is now, in our case, the second joint would be y2. But I've been saying that this screw coordinate is expressed in a space fixed frame, and this would be, and the exponential would give you the motion of this space fixed frame due to the motion of Q1, I mean joint 2. So why is it then moving the green one, not the gray one? With link one. Exactly. So, and that's the important point, because this is all relative, right? Because what we do, we combine these motions, right? Because essentially, to the second link on which the blue link at which the blue second frame is attached. To this body, the predecessor. Now, what I was saying is, okay. What I want to say is that For the blue body, okay? No, what I want to say. Now I got confused myself. When you define, this is what I'm going to say. When you define this co-coordinate of the second joint, okay, you define them in the initial pose of the system, in which all the frames that are attached to all the bodies actually coincide with the inertial frame. And that's why, of course, they are all, I mean, all the exponentials are describing the relative motion of a copy of the inertial frame that is attached to the respective body, but it's the relative motion. Because for the blue one, the frame in which the co-coordinates are expressed is now the green frame, because the green frame was initially the one in which we expressed it, right? And that's why, exactly as you said, the blue one is moving relative to the green one, not relative to the gray one, because the green one now serves as the space fixed frame for the blue one. Okay, now the question is, what happens to the whole system if the third joint is moving? And then I guess the answer is clear, because it's the motion of a copy attached to the brown frame, brown link, the third one, relative to where it started from, right? And then you do the same, of course, and then you have this the motion due to the fourth joint, which is describing the motion of a frame attached to the fourth, the green one, relative to where it started from. Okay. Okay, what's next? There's one left. What happens if you move the last one? And of course, then you get the motion of a frame that is attached to this one. Okay, this is all nice, because now we have described motions. And in particular, relative motions of the space fixed frame due to the motion of the joints, which is not what I'm interested in, because I'm interested in actually the motion of my end effector here. Okay, and that's why you just have to do a kind of a constant transformation, because this is constant. I have to say, okay, what did I get out of this? Out of this xy5 times xy4 times and so on, this product, I mean, this combination of motions, what do I get is the motion of this yellow frame, which is the motion of the frame attached at the yellow link that was initially coinciding with the space fixed frame, which is not what I'm interested in, but there's a constant offset. There's a constant offset that tells me, okay, well, this frame that is initially coinciding with the space fixed frame is somehow positioned relative to my end effector frame. And let's say the red one is the end effector frame, and there's a constant transformation, constant homogeneous matrix that we called A for absolute reference configuration of the last link, which is number 5. And that's A5. So now if you combine all of them, you get exactly what we are interested in. You get H5, right? Because H5, do we say it? Yeah. H5 is exactly this. So you go from here to here, which is A5. Then you go whatever happened because of the motion of link 5, which is the exponential here, and so on, so on, so on. And then you get finally to here. So essentially, the pose of the red frame relative to the space fixed frame is this. Okay? Okay, so are we up? Yeah.
Can you give me an idea about why here? Can you help me to visualize the why here?
Oh, yes, I can. Because this is what we have on the next slide. No, do we? I should. Yeah, we have it here. dy, you mean? Yeah. Should we do it after the t or before the t? No, I'm asking because I'm not the master here.
Yeah, so 5 minutes, 10 minutes break. Then we'll...
Yeah, exactly, because it's all here. But I guess he needs a t. So
no, actually, as per the schedule.
Sure. Okay, then see you in 5 minutes, or I don't know what, 10 minutes.